Every plant, animal, and ocean current on this planet is driven by a single invisible process happening 93 million miles away. Deep inside the sun, immense pressure forces two light atomic nuclei, specifically hydrogen, to collide. When they fuse into a heavier helium nucleus, they release a burst of energy. This reaction produces millions of electron volts from a single pair of atoms. Crucially, because there are no heavy radioactive fragments as side products, the energy released is entirely clean. Curious, if the process is this efficient and produces no waste, why haven't we successfully integrated it into our power grid? The roadblock lies in basic physics. Because atomic nuclei are positively charged, they naturally repel each other. This is called the Coulomb repulsion force. To overpower that repulsion, you have to slam the atoms together at incredible speeds. They need enough kinetic energy to overcome that electrical barrier so the nuclear force can take over. In a laboratory setting, that kinetic energy is derived from heat. To get hydrogen atoms moving fast enough to collide, we have to heat them to 100 million degrees Kelvin. That is roughly 6 times hotter than the center of the sun. Achieving and containing those temperatures on Earth is the primary obstacle to a functional fusion reactor. But out in the vastness of the cosmos, nature has a completely different way of bypassing this extreme temperature requirement. The sun is a massive ball of gas, 73% hydrogen. Its sheer scale creates an intense gravitational crush, packing atoms together with incredible density. This gravitational pressure allows the core to fuse hydrogen at 15 million degrees, a fraction of what we require on Earth, because the atoms are forced so close together they have no choice but to collide. As the hydrogen is depleted, the core contracts further, driving temperatures even higher to fuse helium into carbon, oxygen, and eventually iron. When these stars eventually reach the end of their lives, they scatter these heavy elements across space. This means the iron in our blood and the carbon in our DNA were literally forged inside a stellar fusion engine. We have successfully replicated this process on Earth, but so far we have only been able to do it in an uncontrolled explosion. Without a star's gravity to compress the fuel, weapons engineers had to find a different way to generate the 100 million degree temperatures required for fusion. Their solution was to use a traditional atomic fission bomb as a trigger. In a hydrogen bomb, the fission primary detonates first. This creates the instantaneous heat and pressure necessary to ignite the fusion fuel in the secondary core, resulting in a second, larger explosion. The difference in scale is massive. A thermonuclear weapon weighing 1,000 kilograms can produce an explosion comparable to more than 1 billion kilograms of conventional high explosive. The hydrogen bomb proved that terrestrial fusion is physically possible, but it also highlighted the gap between a destructive chain reaction and a steady, harvestable power source. The goal now is to turn that split-second explosion into a continuous, controlled burn. Scientists are developing magnetic containment systems that can suspend a 100 million degree plasma in midair, preventing it from touching and melting the reactor walls. Success would mean that a significant portion of our global energy could be generated from hydrogen isotopes found in ordinary water. By studying the distant nuclear reactions of the sun, we are learning how to build and contain a